Good evening, everyone. My name is Yan. I'm currently working for a company called Space Ape Games, where I make mobile games for a living, at least for a few more weeks before I go to the next thing. And I'm actually here to talk to you about what happened in 2014. You may ask why, because it just happened to be a very momentous year where lots of interesting things happened. So, for example, Taco Bell launched their first ever breakfast menu, and then Alibaba, exactly right? How could I miss that? And then Alibaba also raised the biggest ever IPO at something like $25 billion, which is actually pretty amazing. But we also had the Grumpy Cat, and of course, everybody was saying, let it go, after Frozen came out. And whilst all these amazing things are happening all around the world, Amazon dared to announce this thing called AWS Lambda. And ever since then, there's been this really fun game that we all played, where one person says serverless, and then someone else says, but there's still a server somewhere, which, of course, just entirely missing the point, because serverless is serverless in the same way that Wi-Fi is wireless. Even though there are still wires, point is you don't have to worry about those wires anymore. So as a community, we argued a lot about, for like a good part of the last year and a half, we've been arguing about what does serverless mean, because it's not a very good name for this technology. But I think eventually we settled down on three things that we can all agree on: that a serverless solution is one where you don't pay for it if no one's using it, and that it is one where you don't have to worry about provisioning and managing servers, and you don't have to think about how you're going to scale your cluster of servers as well. And of course, the most often talked about serverless solution is what we call function as a service offerings, such as AWS Lambda or Azure Functions or Google Cloud Functions. So essentially, you're writing a tiny piece of code, a function, and then you deploy it to your cloud provider, AWS, for example, and then you delegate it to AWS to then call your code whenever some event happens, which could be someone making an HTTP request to an API gateway endpoint, or your IoT sensors is sending a signal to IoT service, or some message being received in SNS or Kinesis streams and whatnot. And compared to other paradigms of building and shifting software in the cloud, you've got your infrastructure as a service, you've got your containers as a service. Fast is closest to, say, your platform as a service offerings like Google App Engine or Heroku. The key difference there is that your unit of scaling is now the individual functions that makes up your application, as opposed to applications themselves, which is the case you will find in the Google App Engine and Heroku. And even though serverless and fast are often used interchangeably, there are subtle differences that are quite important here. For example, if you're using Kubernetes, which allows you to basically build a fast programming model on top of your own Kubernetes cluster, then when no one is running functions on that cluster, you're still paying for the underlying cluster. So by our definition of serverless, it means that Kubernetes is actually not a serverless solution, but it still functions as a service. Equally, when you think about something like S3 or the new Aurora serverless offerings for database and for storage solutions, those are serverless offerings, even though they don't give you the programming model of functions as a service. A lot of people in the industry, people like Simon Wadley, for example, who is, I guess, a noted advocate for serverless technologies, and myself believe that serverless would be one of the, if not the primary way that we build and deploy software in the future, and for good reasons as well. That by and large, a serverless solution is going to be more scalable than what you can build yourself. Lambda, for example, they can spring up something like 500 containers per minute, which is a lot faster than what you would probably be able to do yourself. And also, the last study I saw that looked at the cloud utilization VM utilization in the cloud, found something like more than 2/3 or around 2/3 of VMs running in the cloud are running at less than 10% utilization, which just tells you that a lot of people can save a lot of money by moving those workloads from those idle servers to a serverless platform like AWS Lambda. And also, out of the box, you get built-in redundancy with multi-AZ support as well. So you get a really good baseline resilience compared to what you would do yourself by just releasing your application into EC2 instances running in single region or single AZ. But for me, the big reason for go serverless is that all the things that you can see behind me that stands between you having a great idea to having that idea actually being put in front of your customers and deliver value to your customers, when you use serverless technologies like AWS Lambda, a lot of them becomes irrelevant, or they've been drastically simplified when you use the right set of tools and techniques, which in return means that you can be much faster. You have got this great velocity to deliver features and deliver those nice ideas you have in front of your customers. And because of the cost saving you can have as well, it means the risk of having the wrong idea is now drastically shortened, because you can just easily build a feature on top of Lambda, an API gateway and whatnot, deploy them, and if no one uses it, fine, you just kill these functions. You don't pay for it if no one uses it anyway. So you get this great increase in velocity by removing those undifferentiated heavy lifting, things like managing your own servers and configuring patches to your OS and upgrading them. All of those things, you offload them to your cloud provider like AWS instead. So in return, your developers get to focus on building the things that your customers are looking for you to deliver. I actually did a talk last night at a London DevOps user group to talk about many of the things, what serverless ops would look like. So if you want to see, so if you missed that, then it was recorded at several conferences. Oh, the link is cut off at the end, but I will share the slides after so you guys can go check it out, where I talk about a lot of things I learned in one of my previous companies where I worked on a non-trivial serverless application, architecture for a social network where we use serverless for all kinds of different workloads. And we had to solve all the questions that you have around ops in terms of how do you monitor things, how do you test your functions, how do you do distributed tracing, how do you manage configuration and security and so on and so forth. And one of the things I noticed in this journey that I went on is that event-driven architectures also become much more commonplace when you're talking about serverless technologies. And I think in part thanks to the fact that it's now far easier to build them. Using technologies like Kinesis and Lambda, you can build an event-driven architecture far easier than you've been able to do in the past. And with events, I think they are a great enabler for you to build that composability into your architecture, where you can build different features and compose them together via events, rather than every time you want to build a new thing, you have to update, then deploy existing services in order to create those bridges. And you can use AWS Lambda as a glue that connects everything together almost effortlessly. And over time, you find that certain patterns, certain usage patterns of how people combine Lambda with other services start to emerge. And as should be customary for any talk that talks about design patterns, I should give you a stern warning that a design pattern is not a recipe for success. It doesn't guarantee you anything. By definition, a pattern is just something, a repeated way that something is being done. And it's not a substitute for you really needing to understand your problems and the set of constraints that you're working with. And if you're not careful, as the context in which those best practices and design patterns has evolved in, as they move around, today's best practices can easily become tomorrow's anti-pattern. So always try to understand the problem domain that you are trying to solve, rather than just follow blindly best practices and design patterns. And I guess what I'm saying is that I'm not here to sell you some snake oil or some magic bullet, because they just don't exist. We should stop, as a whole industry, stop looking for those magic bullets. Use the right tool for the right job, and that's it. So with that said, I'm going to share with you some high-level patterns I've seen in terms of how people are using Lambda combined with other services, as well as some lower-level patterns around certain implementation details that you can use, which take advantage of certain traits you find with maybe SNS or Kinesis, how they work with Lambda, and how you can take advantage of those traits and apply them in the right context. So we start nice and easy with cron jobs. So why run a server and pay for it 24/7 when all you need to do is run something every 5 minutes? So instead, what you could do is to use a CloudWatch event, where you can create a schedule that says, in this case, run every 5 minutes, and run animation, and then just call a Lambda function. So you can really easily take your existing cron jobs, put them into a Lambda function, and then use CloudWatch events to then schedule those invocations, say every 5 minutes or every 2 seconds, which is up to you. And in terms of automation, one of the things to keep in mind is that when your Lambda function writes to standard out, all of those things get collected and shipped to CloudWatch logs as log events that you can watch or you can look at. But CloudWatch logs is not easy to search, especially when you have many functions. So in practice, what a lot of people would do is that they will go to the console, they pick a CloudWatch log group, and then say, I'm going to stream all the logs to another Lambda function, and from there, I can then ship those logs to some log aggregation service I want to use, which could be Loggly, could be Splunk, you can afford it. I think I know a few people that use Splunk, and the amount of money they pay for it, just, oh my God, it's crazy. It's so expensive, but very good. But with this setup, that means that every time you create a new Lambda function, it's going to create a new CloudWatch log group, and you don't want to have a manual process whereby someone has then to remember to go to the console and select the log group and stream it to the same function every single time. So what you could do is you can enable CloudTrail, which then opens up a gateway for you to then be able to create event patterns in CloudWatch events, whereby in this case, whenever I create a new Lambda function, the system is going to make the create log group API call against CloudWatch logs, and I can tap into that, I can react to that by calling a Lambda function whose job is to automate the step of subscribing the newly created log group to my log shipping function. So then, wow, okay. So then it becomes like a platform, a capability that I can provide as a platform so that whenever someone creates a new Lambda function, automatically we can expect those logs to be shipped to the log aggregation service at the end of it without you having to constantly remember to do that manual step of subscribing. And this pattern of enabling CloudTrail so that you can tap into system calls that happens inside your AWS account and react to them is really powerful. It allows you to do a lot of things that you may not be easily done otherwise. For example, with CloudWatch logs, another nice little caveat is that by default, the log group is created with the retention policy set to never expire, which quite frankly, it's ridiculous because you are paying for data storage in CloudWatch logs. So that means long term, you're going to end up paying more and more and more per month for logs that you're shipping off to some other log aggregation service already. So that's just silly. So we can do apply the same pattern and have another Lambda function whose job is then to automatically update any log group that's been created to have the retention policy to something like 7 days. And equally, whenever you create API, if it's a convention that you want to apply to your architecture, to your entire team, that whenever someone creates an API in the API gateway with Lambda, you should have alarms around 95 percentile latency on endpoints, and also there should be a dashboard that includes some basic telemetries included in your CloudWatch dashboard. Then you can automate those creation with CloudWatch event pattern and then Lambda function to create those resources, create the necessary CloudWatch alarms and then those dashboards in CloudWatch. And equally, you can capture logins to the console via CloudTrail, so you can automatically alert someone if you see that someone is logging to the console at suspicious times, like 2 a.m. in the morning, or from locations in the world where you don't have any employees. So clearly, something is not quite right. And equally, if you're seeing there's some activity on EC2 in regions that you're not using any infrastructure in, say, Sao Paulo. For my friends at AWS, they tell me that Sao Paulo and Tokyo are the hotbeds for hackers to spawn EC2 instances to do Bitcoin mining once they've compromised their account and stolen your credentials. So those are good places to look out for activities that you don't expect them to be there. And the Serverless Framework guys recently published a survey for 2018 and around usages for AWS Lambda that they can see. And the biggest use case by far is using Lambda with API Gateway to create web apps. So in this case, imagine you have your single-page application, all statically rendered and stored in S3, so it can be exposed to CloudFront. And then on the API side of things, you've got API Gateway and Lambda with DynamoDB as a backend database. And then you have Route 53 as your DNS in the front, so that you have a nice user-friendly URL for your APIs. And you can also then use Cognito, or one of the Cognito services. Okay, I can't really see it. One of the Amazon Cognito services to do authentication. The nice thing about Cognito is that with Cognito user pools, for example, it integrates out of the box a number of user flows you'd expect around registration, sign in, sign out, forgotten passwords, and whatnot. And it also comes with a number of leading practices that, again, authentication is really hard thing to build yourself and to do it right. So, for example, Cognito user pools uses the SRP protocol, which basically says that the actual password itself never gets exchanged between client and the server, only a hash of it. So even in encrypted form, those passwords never exchange hands. And also, it automatically encrypts all the data on the server side, and it supports MFA as well as capture, and a number of other nice, I guess, best practices that you will have to implement yourself otherwise. And if you're using Cognito federated identities, then what you can also do is use a third-party OAuth provider, authenticate, get the JWT back, and then you can give it to the Cognito federated identities, who would then do the validation for you, and then in return, give you back a temporary IAM credential, so that from the client, you can directly access AWS resources, which can also be your APIs that you created in the API gateway and Lambda, and you can use IAM as the authentication method for those endpoints that you create. And equally, if you're using Kinesis or IoT, for example, this is how you can do authentication with AWS Cognito services. But what about multi-region? So there's many reasons for you to want to have multi-region set up with your architecture, serverless architecture, for both performance, by having your infrastructure closer to your customers. You can improve the latency they experience, but also for resilience as well, where you can have active setup, whereby if one region fails, you just shift all of your traffic to another region where everything is still performing correctly. And thankfully, with DynamoDB, you now have global tables where the database itself can also be globally distributed. And equally, API Gateway introduced the regional endpoints. So what you can do now is to basically have the same API created in multiple regions and all talking to the same DynamoDB global table. So if one region goes down, you can just change your routing in Route 53 so that all traffic can be then routed to a region that is still working correctly. And if you want to see how to actually do it yourself, Alex Casaboni from Cloud Academy actually did a very good tutorial recently, which you should go and check it out. Again, the link is not quite visible there, but you can find them on the slides afterwards. Another very common usage pattern with AWS Lambda is to build some kind of data processing pipeline. And as far as AWS is concerned, S3 is your de facto choice for doing data lakes. You can control access via IAM, and you can also do encryption on the server side with KMS. And Amazon also announced a new service last year called Macy, which basically uses machine learning to learn about the content you have in your bucket and tell you that, hey, you've got some user identifiable information, maybe they shouldn't be there. So there's a lot of tools that comes out of the box that you can use with S3. In terms of getting data into S3, quite common, you see people use the Kinesis to do event processing, but then they also then stream all those events into S3 directly using Firehose, which basically means you can get all of this pipeline in place without having to write a single line of code. Because with Firehose, you just say, that's the source stream, that's S3 bucket, you deal with it, and Amazon basically do everything for you in terms of shuffling all the events, batch them up into 5 meg files or file for every 5 minutes worth of data and put them into S3. And if you need to do some additional processing to other features that uses Kinesis events, then you can use them and have a Lambda function subscribe to Kinesis. And equally, if you want to do additional transformation before you save those events into S3, you can hook up a Lambda function with Firehose to say, OK, take those inputs from Kinesis upstream event and do some modification, and then what I transform into, those get saved into S3. And once the file gets dropped into S3, you can actually hook up an event so that whenever a file gets put into S3, it calls a Lambda function with the metadata about the S3 file so that you can do additional processing after it's been saved into S3, maybe by, say, writing some metadata to record them in DynamoDB or Elasticsearch to make it easy for people to see what files you have. And in my case, I've actually done this quite a lot, whereby I've been using Google BigQuery for many years. It's a great platform for doing BI, very, very scalable. And I think I've been using it since about 2011, way before Amazon announced the competitor for that service, to that kind of similar ad hoc queries on the exabyte size scale data set with Athena, which was announced, I think, about two or three years ago. And with Athena, basically, you get this nice ability to run ad hoc query against raw data you have in S3. And then you can even hook up the results with a QuickSight so that you can visualize and chart those data as well. So that's a lot of things that you can do very quickly by combining Lambda with other services. But let's take a moment to look at some lower level implementation patterns as well. One of them is called the couple invocation that comes straight out of the SOA patterns book, which is essentially designed for try to help you answer the question of how do you build a service that can handle massive spikes in load and not fail over. And I also find that it's very good for dealing with business logic that takes a long time to run, potentially very computationally expensive, for example. And for Lambda, it's particularly relevant because when you build an API with API Gateway and Lambda, API Gateway has got a max timeout for 29 seconds. So even though your Lambda function can run for up to 5 minutes, API Gateway is going to stop waiting for an answer after 29 seconds, and it's going to return a 500 to your caller. So anything that's longer than 29 seconds to process, then this is a pattern you should think about. Another thing that this pattern is really good for is when you're depending on some downstream system that's perhaps running on legacy architecture and is not as scalable as your Lambda function that can scale massively in a very short space of time. So what happens then if you're projecting all of your concurrency to your downstream is going to cause your downstream to then become slower and eventually error and cause your APIs to error as well, which is not the kind of experience that we want to give to our users. So as the name of the pattern suggests, what you could do is to decouple the request from the response. So in this case, a client will make a request to the API to say, hey, you do something. And the API will say, OK, sure, I'll return a 202, but so no content, but I'm going to tell you where the result would be once it's ready. In the meantime, I'm going to queue up some work for some background worker who is going to be churning away in the background, whilst the client would then be polling for result. Is it ready? Is it ready? Are we there yet? Are we there yet? And eventually, the worker is going to finish the job and going to tell the API. And then the next time the client polls, the API will say, yep, sure, finally it's done. Here's response with a 200. The idea here is that you can use this pattern to then amortize any spikes in load that you experience, because once you're able to control the level of concurrency you have for the background worker, then that means you can constrain how much concurrency you project onto those downstream systems to the point that you never give it more than it's able to handle. Another nice side effect of this pattern is that even if you're doing something that can be time-consuming, you can still respond to the client very quickly, because again, remember, when you're talking about distributed systems, you can't tell the difference between someone not receiving a message at all or it being down to it just being slow. So being able to guarantee that you should always respond to the caller quickly whilst you carry on at work in the background is also a very useful property to have. And we can also be smart about how we expose those status changes to the client as well. WhatsApp, for example, does this very well. You have different ticks that represents when the message is still in the buffer, when it's been sent, when it's been received at the side, when it's been read, and so on. You can apply similar techniques to how you expose the status of those work that you have queued up in the background. And now that you remove the urgency to respond to the caller within a reasonable amount of time, it means that you can also be more flexible about how you handle retries and failures as well. So let's walk through a simple example. A client makes a call to an API, it gets handled by Lambda, and at that point, Lambda will save some metadata about a task into DynamoDB, and notice that the result says no, so because we haven't got the response, the result yet. So at that point, the Lambda function is going to queue up the task in SQS, and it's going to respond to the caller to say, hey, 202, I don't have an answer for you just yet, but here's a location where the answer would be. And in the meantime, you got in the background Lambda function that's polling from SQS. And you can also easily add some kind of timestamp as well, because you don't want the client to be constantly polling forever without ever timing out that request. So now when a client comes to the API and say, hey, is my result ready yet? You check the database. Nope, you still no, it's not ready. So you tell the client 202 again, and in the meantime, the worker has finished processing, so now it's going to update the record in DynamoDB with the response, with the result. So the next time the client asks for, are we there yet? You can say, yep, it's all good, 200, and here's the response. So one of the things that I guess to keep in mind is that with this pattern, since you are you're trying to control the amount of concurrency you project onto your downstream system. So with Kinesis and with Kinesis streams and DynamoDB streams, the way these streams work with Lambda is such that every single shard you have in Kinesis has corresponding instance of Lambda function. So you can control the level, the degree of parallelism you have with that particular Lambda function by controlling the number of shards you have that stream, so that you don't create more shards and therefore more concurrency than your downstream system is able to handle. Which also means that SNS is a really poor choice as the queue in this case, because SNS, the way it works is that every time you send a message to SNS, it's going to create a new instance for your Lambda function. Therefore, you have a one-to-one mapping of the concurrency that you experience to the concurrency that you're going to project to your downstream. So it entirely defeats the purpose of being able to amortize any spikes in load. So another similar pattern people often use is PubSub, where it's a very popular messaging pattern where the publisher and the subscriber are decoupled through some intermediary broker. And every subscriber receives the same message, they all process them. And I think that as the pattern is very good for decoupling data processing into individual units that can fail independently, which ultimately makes partial failures a lot easier to manage and handle. And again, as the broker, you can use SNS. You may want to use Kinesis streams or even DynamoDB streams or even SQS. And I think the most obvious choice for people when it comes to doing PubSub would be to use SNS, because by and large, you want to optimize towards the degree of parallelism within reasons. And in this case, you also get nice built-in retries and delta queue support for Lambda between SNS and Lambda as well. So if your function invocation fails, then SNS will retry the invocation twice. And then if there's a delta queue configured on the Lambda function, then you also then put the event and put it into a delta queue as well. So there's a chance for you to then go back and investigate what happened. Why did those events invocation fail? As we just mentioned, with SNS and Lambda, it's one invocation per message you receive. So if you send 100 concurrent messages to SNS, you're going to have 100 concurrent executions for your function, which means, again, in terms of that concurrency, is now one-to-one mapping for what you send to SNS to what your downstream services experience. So that's something you need to keep in mind. And also with SNS, you can actually quite easily DDoS yourself when you have some processes that are spamming SNS and now it's creating tons and tons of concurrent executions for Lambda. And remember, Lambda's got a default limit of 1,000 concurrent executions per region. So when you're doing that, it's actually a friend of mine, happened to a friend of mine this week that they accidentally DDoS themselves when one service failed and just continuous retry storm by sending messages to SNS, and then that creates tons and tons and tons of Lambda functions. I think they end up running into something like 1,400 Lambda function invocations per second on a fairly low traffic system. Again, with SNS, you can suffer from temporal issues like the ones we have discussed so far, whereby if you have a spike in messages, in the messages coming in, then you can cause some of those invocations to fail. Luckily, with the retry, so if your spike is very short, that means by the time they get retried, chances are you will succeed, which is great. But what happens if that spike is sustained over a longer period? Then you can still exhaust the number of retries in that time. And also, what happens if your downstream system is out? So if you're experiencing, if you're using, say, SQL database as a backend, and that server is down for maintenance, then any message that's received and processed and retried within that window are all going to fail. Doesn't matter how many times you retry it. And if you have delta queue, then great. At least you can recover those messages and hopefully retry them again later. And with Kinesis, then you have that protection against temporal issues. Again, with Kinesis and Lambda, the way it works is that when your Lambda function posts Kinesis for a batch of records, that's also one important difference as well between Kinesis and SNS, in that SNS is always one message, one invocation, whereas with Kinesis, you get them in batches. So partial failures becomes much more difficult when it comes to SNS, where, okay, I've got a bunch of records. 9 of them was fine. 1 of them failed. What do I do? If I fail the function, then the next time I'm going to get all 10 of them back. Do I reprocess everything? Do I make sure that I have idempotency in my system, which may be easier said than done? Or do I do something clever? which there are actually several ways you can get around this, which I've written about in the past, so feel free to come and talk to me afterwards. But with this behavior, it means that you can just keep on failing until either the data has expired from the stream altogether, or your function eventually able to process the event successfully. And as mentioned earlier, with Kinesis, every shard you have in the stream will have a dedicated instance of Lambda function doing the polling and processing. And it means that when you have temporal issues like the ones we have just discussed, you can, for starters, you can amortize any spikes in load so that you don't expose too much concurrency to your downstream system. But also, if your downstream is having an outage, Kinesis will just keep on retrying until eventually your downstream system comes back online and it will just continue from where it was failing before. And inside AWS, besides Kinesis streams, you also have DynamoDB streams. So that means that whenever you write something to, or whenever you update your DynamoDB table, then there's an event, corresponding event that happens in the DynamoDB stream that you can react to. And I guess the question of whether or not you should use a Kinesis versus DynamoDB streams, and the biggest question I would say is, what's your source of truth? If writing something into a DynamoDB table means that is not canon to the state of your system, which is I guess the case for most systems you see. But in an event source system whereby the state of a system is modeled as a sequence or a sequence of events as opposed to snapshots, then the source of truth may be the individual events. Once it's been written into the stream, then that event becomes canon to the state of your system. So that's a question that only you can answer depending on how you've modeled the state of your system. A couple of things to keep in mind with DynamoDB. Firstly, the events you're going to get from the stream is going to be limited to only the type of data that you store in that particular table. And that the events you're going to get, they're going to describe events that are particular to DynamoDB, item being added, item being removed, item being updated. They're not going to describe events that happens in your system, which should be user being created, user profile updated, user change their profile image, and so on. Which for me always creates this mental dissonance that I've got to map from what I see in the DynamoDB stream event to what it actually means in my system. And that's one reason why I don't like working with DynamoDB streams. In terms of operational-wise, DynamoDB streams, interestingly, auto-scales the number of shards, which is completely different from Kinesis streams. On its own, I think it's such a good thing. That means you don't have to worry about, and in fact, I had to build auto-scaling from Kinesis in the past myself because we don't get that as a feature from the platform. With DynamoDB streams, you don't have to worry about that. On the flip side, it means that, remember we talked about having control over the degree of parallelism so that we don't expose more concurrency than the downstream can handle. DynamoDB streams is going to auto-scale, doesn't matter how much your downstream system can handle. Also, with DynamoDB streams, you can't extend the data retention policy to more than 24 hours. With Kinesis, you can pay extra money to have data in the stream stay around for up to, I think, 7 days. In terms of cost, Kinesis charges you based on shard hours, as well as the number of pull requests to the stream, whereas the DynamoDB charges based on the number of read requests. But interesting caveat is that when you're reading from DynamoDB streams from Lambda, it's actually free. So that means you're still going to pay for the read and write throughput units, but it means that when you're using the streams on top of that, then it actually becomes free. So let's look at the cost a little bit. When you're talking about 1 message per second for a month, assuming that every message is only 1 kilobyte, you can see that DynamoDB is actually really, really cheap. It's like 47 cents by comparison to Kinesis, which even if it's just 1 shard, you're going to be, can you see? I don't know if you guys can see. You see 47 cents because you're only paying for 1 write throughput unit capacity for that table. What happens if we scale this up then? All of a sudden, it looks quite different now, doesn't it? That the DynamoDB for 1,000 messages a second for a month is going to cost you $470, which is still not that much, to be honest, because you're only paying for 1,000 write capacity units. But again, that depends how much your overhead, how much buffer you want to leave yourself. And again, with SNS, you can now start to cost you a lot more money when you're talking about a large number of messages per second. Of course, these are just estimates. They make a whole bunch of assumptions when I come up with these kind of numbers. But the thing to keep in mind is that with Kinesis, even though there's a baseline cost for one shard, at least you can't have a stream with 0 shards, because the cost for pull requests grows much slower compared to other services where you're only paying based on request count or the number of write throughput units, then when you are at scale, Kinesis can be a lot cheaper. In fact, one of my previous companies where I build a mobile game that's got 1 million daily active users, one of the things we looked at when it comes to deciding between SNS and Kinesis, this is way back before Lambda, was that fact that Kinesis at scale is a lot cheaper than, say, SNS. You don't have to stop there either. You can stack one pops up with another pops up by having a Lambda function, then publish messages to other destinations that are perhaps not supported natively by SNS. The downside here is that now you're taking on the task of managing those failures and partial failures and errors. So what happens if you send a message to your API gateway, that failed, but everything else was successful? What do you do then? Now you got to take on that complexity of managing those retries and how to deal with those partial failures. And the last pattern I'm going to talk about, I promise I'm going to be done soon, is the Saga pattern, which is a pattern for managing failures inside a transaction when you have a distributed system. And this is a pattern that has been around for a very long time. I think the first paper on this pattern was in 1984, something like that. And Katie McCaffrey, I think she's still at Twitter, she did a very good talk on this 2 years ago at GoTo conference. So again, go check it out after tonight. So using her example from her talk, imagine you are building a travel site, and one transaction could be booking a hotel, then booking the flight, and then booking some car rental. So now imagine if one of those actions failed. So you booked the hotel, that was okay, but now you're booking a flight, that failed for some reason. So now you've got to cancel out the booking for the hotel as well. So in that case, you can model those actions, like booking a hotel, with compensating actions, i.e. rolling back and canceling the hotel booking with Lambda functions. Both the actions themselves can be functions as well as the compensating action or rollback actions as functions. And then you can use AWS step functions, which I don't have time to talk about, but it's one of the services that Amazon introduced, which basically allows you to create a state machine, and where every single step in that state machine can be a Lambda function invocation. So you can imagine that your state machine can look something like this, whereby, say, based on some input where I want to go to holiday in Dublin and stay in the Holiday Inn. I don't know why I would want to do that, but imagine the happy path would be booking a hotel, all good, flight, all good, rental, all good, transaction done. But what happens if I book the hotel and then I book the flight and thus, oh right, okay, you can't read, the color is a bit messed up, but I booked the hotel, it's fine, booked the flight, that didn't pass for some reason, so now I got to perform the compensating action to cancel whatever other state I've changed as part of that booking, but then also have then move on to the next state to cancel out the hotel booking as well. And then that will fail the transaction, as you can see at the bottom there as a fail. In fact, I put this onto GitHub as well, so you can go and check out the code base. It's a very simple state machine that just gives you, I guess, an idea on how you can apply the Saga pattern with a state machine, step functions, and Lambda. So that's just over time, and thank you very much. A lot of things I've talked about I guess now and then in other talks have been put together into a video course with Manning, so go check it out as well. Whilst it's in the early access program, you can also get 40% off. Again, thank you very much for having me tonight.